So we're going to try to describe the Brownian motion as a process, and to do this we're going to start off with something much simpler. We're going to start off with a discrete time Markov chain, and more specifically a random walk on a network, actually a very special network, the network where the vertices are the integers. So I've drawn them here. So you have, the integers are 0, 1, 2, 3, all the way out to the positive infinity, and -1, -2, -3, all the way out to negative infinity. So that's going to be our state space, or the vertices. And the edges are, you can see how I haven't drawn all the possible edges. I'm only drawing an edge with weight 1. All the edges are going to have weight 1. If and only if the difference between the two states, these are my two integers, is 1. So the difference between 2 and 3 is 1, so I placed an edge here. Difference between 2 and 1 is 1, so I placed an edge there, so on and so forth. And so what kind of description do you get from this a random walk? Well, we know it's a Markov chain. Every random walk on a network is a Markov chain. And to compute the transition probabilities, well, you're gonna, what's the probability of moving from 1 to 2? Well, it's this edge weight divided by the sum of the edge weights coming in at 1, so it's 1/2 to go from 1 to state 2, and it's also 1/2 to move from 1 to 0. And same thing with 3, going from 3 to 4 has probability 1/2, and going from 3 to 2 has probability 1/2. These are my, in other words, these are my possible transition probabilities. I can go from any integer x to x plus 1 or to x minus 1. Each is going to have a transition probability 1/2. And usually the way this is written is as follows. S is the process I'm trying to describe, the random walk. And at time k, it's just a sum over a bunch of what are called increments. Every xj there is an increment, how much the random walk moves in one unit of time. And these increments are IID, so they're independent and identically distributed. And the probability that we move either left by 1 unit or right by 1 unit is 1/2, which is exactly what comes out of the network description of things. So these are just two different ways to talk about the same thing. In one case, I'm talking about a network with a bunch of vertices and edges, and we're moving with equal probability between the two neighbors. And here I'm writing it explicitly as a sum of a bunch of increments. Every increment is either +1 or -1. If I'm moving left, it's -1. And if I'm moving right, it's +1. And therefore, of course, given that I start in an integer and my movement is always in increments of 1, whether this way or that way, in the end, this Markov chain is going to have, is going to be valued in the integers. So, those are kind of two different descriptions of the same thing. Hopefully, you can argue why it's a Markov chain. You can try to write out the transition probabilities as I've done here and assign them the actual probability value, so 1/2 here and 1/2 here. Neither depends on what happened in the past. It doesn't even depend on what the current state is, which is perfectly okay. So here, this is not just a Markov chain. It, not only does it not remember, the past. So if it's at state 3, the transition probability of going to 2 or to 4 are both 1/2, and not only do they not depend on 3, they also don't, of course, depend on anywhere where I was previously. So it's certainly a Markov chain. So just beware that these transition probabilities don't always have to depend on the state where you are. That's actually perfectly okay. And in this example, there's no dependence on where we are. The reason it's a Markov chain is specifically because it doesn't depend on anything in the past. You're allowing it in general to depend on x, but here it doesn't depend on x or anything that came before. So, why am I kind of setting up this model here? Well, it's what it's representing, and going back to this video here. What it's representing is the movement of our Brownian particle, but in one dimension. This is actually the way Einstein did it in his 1905 paper. There's no kind of, you know, there's nothing to be gained from looking at 3 dimensions. It just makes it more complicated. We can think of, you know, a liquid in 1 dimension, and we can think of that blue molecule there moving in 1 dimension. And so why does it move back and forth so along these vertices kind of in this random fashion? Well, you can think of every move corresponding to the particle getting hit from the left or from the right. So if I'm at 2 and I get hit from the left, I'm going to move over to 3. And if I'm at 3 and I get hit from the right, I'll move back to 2. If I get hit from the right again, I'll go to 1. And the idea is that this liquid where the particle is suspended it's uniform. So there's no, what's usually in the literature called drift. There's no drift here. And so I'm equally likely to get hit from the left or the right. These particles are sort of just randomly moving. They're not flowing in any one direction. So there's no kind of preference for left and right. You're moving either which way with a probability of a half. And so it's kind of important to keep in mind as to, you know, when you actually move, you know, this way or that way, it corresponds to this blue particle getting hit from, you know, the left or the right. In other words, being bombarded from the left or the right, and that's what's causing this jagged motion. And we're, you know, just thinking about it in 1 dimension, but there's nothing to prevent you from taking your network to be Z3. So then you'll have 3 coordinates, X, Y, Z, and, you know, in each case you're going to be hit from, you know, one of 6 sides, you know, up, down, left, right, back, front, and, you know, all the probabilities with these increments are going to be exactly the same. These x's, these increments are actually going to be vectors, or, you know, kind of tuples of size 3, and so on and so forth. So it's, you know, an easy generalization here. So, you know, the main issue that we now kind of face is that, first of all, you know, this movie here, you know, number one, you know, it's moving in the way we experience time. So time is continuous. We experience time continuously, not in increments of, you know, not in step increments. And so that's one issue. And the second thing is that the position of this particle, it's clearly not moving on an integer lattice, right? It's not moving in these giant increments. Its path seems to be continuous. And so our job here is going to be to move from this discrete time, discrete space Markov chain model over to continuous time and continuous space. What I've done here on this side is to try to take kind of our first step, which is to move over to continuous time. And, you know, to do this, I'm going to define this increment of time. So an increment of time is, you know, you can think of it as the amount of time that it takes for this particle to get displaced. So it's getting hit from the left and the right, and every time it gets hit, a small amount of time, delta t, passes, during which it gets displaced. In our one-dimensional case, it gets displaced either to the left or to the right, and we're going to say it's going to happen in this small increment of time, delta t, and we're going to take this delta t down to 0. In fact, we're going to make it smaller and smaller and smaller. What I'm accomplishing by doing this is actually transitioning to continuous time. And you know, the way to kind of rewrite what S was on the left side of the board over to the right side of the board where I have continuous time. And this picture, right, this picture corresponds to this one right here. I'll discuss both in a second. You can see kind of how I convert from continuous time to from continuous time to discrete time as follows. So, you know, if t is going to be my continuous time index, so something in 0 to infinity, a real number, and my delta t is going to be some very small increment in time during which this particle gets, you know, bombarded or moves over to the left or to the right. The number of time steps is going to be just t divided by delta t. Right? I took time t, and I had, you know, every single time I had delta t time, so the number of those steps, the number of bombardments, is going to be t divided by delta t, and I put these brackets around here to indicate that I'm going to have to take the integer part. So why do I take the integer part? Well, you know, I had a discrete time process here, so I need to convert this thing here to the closest, you know, natural number. t divided by delta t could be 3.567, right? I'm going to take the integer part, which in this case is 3, and that's what these brackets mean. So the integer part of pi is 3, the integer part of 2.99 is 2, and so on and so forth. So integer part is always going to be smaller than, you know, whatever this gives me. But, you know, that's kind of the sacrifice there. I'm not completely being accurate, but you know, I pick up the fact that I get a discrete time step, which is what I need in order to relate kind of what I'm doing here with what we've done on the left side of the board, the kind of initial setup. So you know, now we can kind of look at two of these pictures. This is a picture of, you know, potential path of this random walk in time. So time is discrete on the x-axis. On the y-axis we have z, the integers. I've started over there at 0, then I moved over to 1 at time 1, I moved to 2 at time 2, I moved down to 1 at time 3, then by time 6 it looks like I'm in integer 4, state 4, went down to, you know, state 2 at time 8, and so on and so forth. And, you know, here I've kind of, I don't know what time this is, 9, 10, 11, 12. At time 12 I hit 0, and then became, you know, the random walk became negative, so it, you know, transitioned from 0 to -1, and so on and so forth. And, you know, kind of the obvious thing to do is to move over to continuous time. Well, you know, I just connect all these dots, you know, together in sort of the obvious way. So I've done the exact same thing here. At 3 I was in state 2, just like on the left, and between any 2 points I could draw a line. So that's what I've done, and that's what, you know, this, at least so far, that's what this looks like. And here is just a little bit of algebra to try to rewrite the discrete time random walk, or Markov chain S, at time k, to write it at as S at time t. And how do I do it? Well, I keep the same, you know, I want to basically keep the same number of increments as here, so as I did over there. So I'm summing up from, you know, increments from 1 all the way to the number of time steps that I've taken, and that's t by delta t, total time divided by, you know, how much time passes in between each displacement of the particle. And so, you know, this part matches the k on the left side of the board. And what I've added here, and I don't know why this is a minus, this should be a plus. What I've added here is, you know, the mistake I made when I truncated this to the integer part. So, you know, t divided by delta t was, you know, maybe 3.56, and I've rounded it down to 3 by taking the integer part. And now I need to kind of connect the rest of the pieces. What's left over from 3 to 3.56? Well, it's the 0.56. That's what I've computed here. So this is how much time has passed if we're only counting in increments delta t, and t minus that is exactly my remainder, my 0.56. And so I've added this and multiplied it by the next increment, or, you know, I guess the current increment. So I've counted up to time step k here, and now I've taken the next increment, which is k plus 1, and I've multiplied it by this, you know, by this interpolating kind of line here, in my example 0.56, to kind of shift over, right, to interpolate between any two successive integers. So now on this side of the board I can ask, where is my s at time, you know, 6.5? Time 6.5 is here, and this line here is downward sloping. This part right here is accounting for the fact that I can actually fill in at time t all of these values, whereas here the question, where is the chain at time 6.5, just doesn't make any sense, because I haven't connected these discrete time steps into any continuous notion or experience of time. And so, you know, notice first of all, this is, you know, very different than what we did in the case of continuous time Markov chains, and, you know, it's for good reason. So first of all, just to kind of revisit this very briefly, when we took a discrete time Markov chain and moved it to continuous time before, by calling it a continuous time Markov chain, we've said it's going to remain flat, you know, on these, you know, in between these waiting times. So, you know, the chain starts at x, then it waits for some exponential amount of time, moves to state y, waits an exponential amount of time, goes to z. That's what we did with continuous time Markov chains, but you know, if you look at the Brownian motion, you'll be immediately convinced that we can't use the same type of model here, because the path is truly continuous. There aren't any jumps, no discontinuities. So the path that you see being drawn out there looks nothing like this, but you know, it may not look completely like this, but we're closer. And you know, what's really missing here is that the continuous time part is there, but I'm not capturing sort of the motion in between. I'm using linear interpolation to approximate where this Brownian motion could be in between 2 and 3, but I haven't done anything to kind of fill in what actually happened in this time interval. So the position of the Brownian motion is going to be in R, the real numbers. Here it's going to be in R3, a three-dimensional cube, but we're going to stick with one dimension. So the next task is going to be to take x, put it into the real values, and leave the integers. We're going to leave this representation, and we're going to and we're going to transition to the chain taking values, you know, in all of R, and fill in all of the missing kind of pieces of the trajectory of the Brownian motion in between these, you know, the time steps, you know, 3, 4, 5, and 6. So that's our next. That's going to be our next step.